Oh yeah, what's kinetic energy? Wait. Alright, so what's gravitational potential energy?
Big G.
What's the one for big G? Yeah, very good. R, not R squared like I keep writing on the board, right? Oh, sorry. What's electrical potential energy?
Get on your game.
Oh, my game.
Yeah, man. Messing me up.
Electrical potential energy.
Over R squared.
K, Q1, Q2 over R. Very good. Just like gravitational potential in the general form. And what's our only other one? Spring, right?
Yeah.
1/2K x squared, right? Okay. And then we have our equations for work. FD cosine theta or F delta R cosine theta. One of those varieties, right? Okay, excellent. So it's not that many. It's kind of an easier way to start than doing kinematics. You probably did kinematics last year first, and when you did that, it was rather challenging to remember all the kinematics equations sometimes. Okay. So it looks like this. You've got a block M, has a mass M. Okay, starts up here at point X. Here's point Y. Here's point P where it stops. Okay, so it slides from here to here. And when it slides from here down to here, there's no friction. Along this part, it's rough, so there's friction. And so it slides down here and speeds up, and then it slides across here and comes to a stop. Okay? I believe is the essence of the problem. And from here to here, this is a radius R. This is a quarter of an arc, or quarter of a circle there, right? All right, so it says, determine the speed of the block A when it arrives at point Y. Okay, going from X to Y. Did we get this far last time?
We were about to do C.
We were about to do part C?
Part C. I did B. We're on part A.
Seeing as we can't agree on where we ended, how about we redo this part?
Awesome.
So part A is, what's its velocity when it gets down to the bottom at Y? Okay? So here we are at Y. Comes down here, slides down here, and its velocity. Okay, obviously we've only covered energy so far, right? But let me explain why. Remember last year, why we don't want to use some of the stuff from last year. Okay? You could figure out the forces on this block. And you could figure out its acceleration. And knowing its acceleration, you use kinematics to figure out how fast it's going here. Except there's one big problem. Will the forces on this thing be constant as it slides down here? No. So will its acceleration be constant? So if its acceleration isn't constant, we can't use all those constant acceleration equations we derived last year, right? Pre-AP physics. How do you know the forces won't be constant?
Because the angle is changing.
Yeah, because what's happening is gravity is the same all the time as it slides down. But that normal force pushing on it varies as the angle changes, right? So the forces won't be the same. So whenever you have a problem like that, where it looks like the acceleration is not going to be constant, therefore it's going to be a challenging problem, think energy. Think, can I solve it with energy or work equals change in energy? Because if so, it's almost always the easiest way. And the reason why it's easiest is because it's a scalar concept and all you care about is the beginning spot right here and the ending spot, right? And all you do is connect those two spots together. Let's do that. Can we use conservation of energy from X to Y?
Yes.
Why?
There's no friction.
There's no friction, there's no net non-conservative forces, right? So the energy at 1 will equal energy at 2. Or I should say energy at X equals the energy at Y. All right, we could have kinetic, we could have gravitational, we could have spring, we could have electric potential energy at location X. We could have kinetic, we could have gravitational, we could have spring, we could have electrical potential energy at Y. Now I'm writing this out on purpose, okay, because none of you will do this. And as I wrote it, you're like, oh my gosh, did I miss something, or has he just lost his brain? Okay? But the reason I'm writing it this way is because I want you to remember most students end up coming up with the false idea that you have one energy to start and you equal with one energy at the end. That's not always the case. The only reason we start with one here and end with one here is because the other ones happen to be zero. They don't always have to be zero. Okay? So just be aware of that. There will be problems that will show up where you'll have like 2 or 3 energies here might equal 1 over here. Or 2 here might equal 2 different ones over here. Okay? Alright, so we start off at rest, so that's 0. There's no springs, so that's 0. We don't have any charges that we know of, so that's 0. So we start off only with gravitational at x. We're moving at the bottom, but we're now at what we call height equals 0. We're at our 0 spot, so that's 0. No springs, no charges that we know of. So we end up with kinetic at the end, right? So we end up with mgh equals 1/2 mv squared, and then magic occurs. The m's go away. And so v equals 2gh square root, except we don't know what h is, or do we? That happens to be r, right? That's our total height, r. There you go. So there's the answer to part A. So now we go to part B. And I think this is where we ended up last time. Part B. It says, determine the thermal energy that is generated as the block moves from Y to P. Okay, thermal energy. So we have a non-conservative force, friction, that's going to take our energy away and turn it into heat, right? So what kind of energy do I start with at Y? Kinetic? And what kind of energy do I end up with at point P? Oops. Sorry. Thermal. Now, sometimes they'll write that as Q, which is the heat. The heat that's generated. If you remember that from chemistry class, Q is heat. And so, wait a minute, all we're looking for is this number right here, right?
Yeah.
So all we need to know is that number, right? But that number also equals the gravitational potential energy at x, right? So all of those are equal, right? So we start off with gravitational, it turns into kinetic, and then it all turns into thermal, right? So you can pick any one of those points and make them equal. So I'm going to do mgh just because I can. So my thermal energy is, my heat that's generated at point P is mgh. Uh-oh, I messed up again. That's not going to get full credit. What did I do wrong? Ah, very good. This is R, right? There we go. Now, for those of you that don't want to solve it that way, for those of you that see it this way, that's okay. If you see it this way, kinetic energy at Y equals the heat that's generated at point P. So that's, what do I put here? 1/2 mv squared equals the heat that's generated. Alright? But I can do better than that. What's V? So I get 1/2 m 2gr. It's square rooted, but then it's squared, right? Oh man, look at that. Same. Okay, no matter which way you work the problem, as long as it's a valid way to think about the problem, you should get the same exact answer, right? And that will happen. So just because your neighbor maybe works it a different way than you, that doesn't necessarily mean that what you did is incorrect. Does everybody see how these two are the same?
Did you plug in 2GR for a V squared?
Excellent. All right. V equals 2GR square root, because that's what we got from part A. And then when I square it, it just becomes 2GR. Got it? Excellent question. Excellent question. All right? Now, a lot of students would have left it this way. If you'd have left it this way on the test, you would have gotten a point for realizing that these two are the same. And that's probably all you would have gotten, because you might have gotten a point for this, but you probably would not have gotten a point. Well, you wouldn't have gotten a point because you didn't substitute this in, and then you wouldn't have had the correct final answer. Because remember, it said in the problem to put everything in terms of M, L, R, and G, right? And whatever other constants are given. Okay? So that's why you wouldn't have gotten full credit. So make sure that you take it back to its most basic symbols. Now, how many of you like symbol problems?
Sure.
1, 2, 3. How many of you like numerical problems? Well, problems with numbers instead.
Need it.
How many of you just don't like problems? Oh no, you're in trouble. That will be a problem. All right. As we go on in this class, I'm going to work the problems most of the time just in symbol form, and then we'll put the numbers in later. And I suggest you do the same thing for two reasons. One is it expands your brain, and you find out things you didn't know before. You find out that things cancel along the way. Like if you just plugged in numbers right away right here, you would be doing extra work instead of canceling out M. All right? So make sure that you put symbols down and cancel things out. It really helps. The second thing is if you work it in symbols, it forces you to go step by step, and it helps you eliminate mistakes. I know most of you are very proficient with your calculator, and you love your calculator, and your calculator loves you. But your calculator is a silly little machine, and it only tells you what you put in it. Okay? And it's easy to make mistakes when you have a really long problem. And when I say long, I mean this was not very long. You could have probably done that one in your head, most of you. Piece of cake. But there's just lots of places to make mistakes. And the last thing is on the free response portion of the exam, is if you just write the answer, remember, you won't get full credit. I think I talked about that in here, right? Okay. So you need to put it step by step, and you'll get a much better grade. It's always sad to have a student get like a 2 on the exam, and they just did it not because they got a 2, not because they didn't know enough, but because they just didn't show enough. Okay? All right. So let's do our last question. It says, write an expression for the frictional force that brings the block to a stop. All right. So now we're trying to find the frictional force. Okay? I want you to think about it. Talk with your neighbor. I want you to discuss how you're going to find the frictional force using what we know already. Okay? That means talk about the problem. Here, we had a really great question. The question was, well, which equation do I use? And we came up with this equation for friction. We said the friction force was equal to the coefficient of friction times the normal force, right? Or it's, okay, we're kind of dredging things up from last year, but the friction force is less than or equal to if it's static, right? And the friction force, if it's kinetic friction, sliding friction, it's kinetic coefficient of friction times the normal force, okay? Well, we got a couple problems with that. No matter what kind of friction is, whether it's static or kinetic. By the way, when it's sliding across the ground, will it be static or kinetic friction? Kinetic. So, okay, we don't have to worry about this less than or equal to thing because this is not the equation we'll use this time. But why are we having problems with using this equation to find out friction? Yeah, we don't know what the coefficient of friction is, right? Okay, now this is going to happen all the time during your lifetime. I'm sorry to tell you that you're going to have a great idea. It's just not going to get you where you want to go. Like, this is a great idea. This would find friction. And we could even find the normal force. Because when it's on a horizontal surface, then the normal force and the gravity force will be the same in this case, right? That's not always the case, but in this case, that's true. The problem is we don't know what that is. We just don't have that information, right? So, while this is a great idea, it turns out to be a dead end. Okay? When that happens, okay, don't give up. Just back the truck up and start down a new avenue. Okay? Just try a different method. So let's go back. What do we know so far? We know about kinetic, gravitational, spring, and electric potential energies, right? None of these have friction in them. So none of those are going to help us directly, it looks like. Okay, we know about thermal energy. We don't have an equation for thermal energy, right? So we know that energy 1 equals energy 2, conservation of energy when? When is that true? If there's no friction and none of these non-conservative forces going on, right? At least no net non-conservative forces, all right? So the non-conservative forces cancel out or they're not there. Okay? Now, do we have that in this case? When it's sliding along, do we have this going on?
No.
No, okay. So when we don't have this going on, what do we have to use in its place? Oh, somebody said it. What is it? Work equals what? It equals F delta R cosine theta, but it also equals... Very good. How much the energy is going to change. All right? How much the energy is going to change. All right, so let's think about it. Because this is by far the hardest problem we've done so far. Let me erase this stuff so we have some room. All right. So work is this, FR cosine theta, and work also is the amount of energy it changes, that transfers, right? Okay, so now when we look at this, here's our object. Our object is moving to the right. What are all the forces on this object as it's moving to the right? There's a gravity. F sub G, there's a friction. Which way is friction? That way, right? So force of friction, and what else? And there's a normal force, right? Or F sub N, if you prefer. And that's it, right? Okay, which of these forces is doing work? Just friction? Yeah.
Friction. Just friction.
Why just friction?
Because everything else is cosine of 90 degrees is 0.
Okay, there are a couple of ways you can argue it. One way to argue it is that since it's moving this way, displacing to the right, does everybody see that you have a 90-degree angle here for this one to the way it's moving, and a 90-degree angle here to the way it's moving? So when I take the cosine of 90, I get 0 for those two. So no work is done for this one and this one. You could also argue, well, wait a minute. This force and this force are exactly the same but in opposite directions. So won't they just cancel each other out and do no work? And the answer is yeah. Those two will cancel each other out and do no work. So you could also argue it from that standpoint. So the only force that's doing work is friction, right? Okay, so friction. Let's put that up here. So we have force of friction right here. How far is it moving?
L.
Oh, very good. It's moving from here to here, which on our piece of paper was L. What's our cosine theta?
-1.
Ooh, why -1?
Because it's a 180 degree.
Yeah, because it's going that way, but the force is that way. So it's a 180 degree. So that's a cosine of 180, which is -1. I'm going to write it over here. Most of you will just put a negative out front, but I'm going to put a -1 to remind you that that is where it comes from. Okay. What kind of energy is it changing?
Kinetic.
Yeah, it's taking the kinetic away, right? It's taking the kinetic away. So it's changing energy, but it's taking our kinetic away. It's making our kinetic
Go down.
go down. So kinetic final minus kinetic initial. What's our final kinetic energy?
K and T and K. Oh, final? Zero. Zero.
Yeah, it's come through rest, right? So it's 0. And that's its initial kinetic energy, right? Okay, now. This is going to be then -1/2 mv squared. Or does somebody have a quicker way of writing what that initial kinetic energy is?
Equals potential. Negative.
Yeah, does anybody see it? The kinetic energy it has here is the same as the potential energy it had here, right? Which is going to be
Negative.
mgh, right? Because if you do 1/2 mv squared again, you plug this v in here, you're still going to get mgh again, right? Just like we did last in part B. So this turns out to be -mgr. mgr, right? Instead of h. We okay with that? Because I kind of skipped a couple steps. Did I lose you? Okay, let me show you. This is 1/2 mv squared, right? But what's v?
Oh yeah, I got that part, how we got to there. But how did we get the change in kinetic?
Oh, how did we get to here?
Yeah, from
Okay.
E.
Okay, because the energy here and the energy here, the difference in the energy between those two spots. Now, remember, we're thinking of the work done by friction. It's going to create thermal energy, but what kind of energy is it taking away to create that thermal energy? Well, it's taking away kinetic, right? So that's why I go, it's changing the energy, it's changing the kinetic energy. Does that make sense? It's taking the kinetic energy away. So the final minus initial, because that's what delta means, final minus initial. So final minus initial, but our final is 0 because it comes to a stop. Okay, so that's where I'm getting all this stuff from. Because there's actually a lot of steps in this one, right? A lot of steps for us to get lost. And then are we okay with this then, turning this into this? Really?
The negative K initial is from problem A. You just grabbed it. Or like
Yeah,
Y.
this is our K initial. You know what I should really do? Is I should really do this to not confuse everybody. From Y going to point P. This is from Y going to point P. So this is the kinetic energy at P minus the kinetic energy at Y. Does that help out?
Yeah.
Okay, because that tells you exactly where we're at. Thank you. Thank you for asking the question, because I'm sure that helped everybody. Okay? All right? Okay.
So it's because it's pulling back frictions. Or you could say it's cosine.
All right, so let's put it all together. This is our work.
We know that negative force of friction times the length is equivalent to negative mgr.
Yes. So this is our work right here.
It's just that it's the change in direction.
This is our change in energy right here.
Either way, it's negative.
Okay? So we end up with force of friction times L, negative, equals negative mgr. The negatives go away. And I'm left with force of friction equals mgr over L. Okay? The cool thing about work and energy is that the math is not challenging. But not really challenging. Not like vector math. But the thought process sometimes can be a little brain numbing. Okay? So, let's answer your question about power first. Okay? Power is the rate at which work is done, and since work changes the energy of a system, power is also the rate at which energy is being transferred or being converted from one kind to another. Okay? Now, power in mechanics, which is what we're studying right now, this study of mechanics, which is forces and energy and momentum and all that, is not used a great deal. It comes in handy now and then. But power comes in really handy when we get to circuits, because it's a real easy way to work with circuits. All right, so here we go. Power.
Is power an equivalent of
Yes. Yes. Rate at which work is done. Okay? Okay, so it's, okay, for those of you in calculus, then power equals dW dt. Rate at which work is done. For those of you not in calculus, power equals delta, or I should just say W, the work, the rate at which work is done, dt. Okay? How much work is done in a certain amount of time. Okay. So, for instance, if I take my lunchbox and I lift it, did I do work?
Yes.
Yeah, sure. Because I changed the potential energy, right? So if I do this versus this, same work?
Yes.
Same work. Same power?
No.
No. Not same power. Power is how fast you do it, essentially, right? So, what's our equation for work? Now wait a minute. Oh my gosh, what's that?
Velocity.
That's a velocity. So it is also FV cosine theta. The force times how fast the object is being moved is... Careful. Don't hurt yourself.
Don't know what that is.
How much energy is that?
So say you're in your car. You're driving along at 80 miles per hour. And let's say that the force required to keep you going that fast is, I don't know, 600 pounds of force. Okay? Now, assuming the force is in the direction you're going, you can find the power output of your engine. It's a pretty good bet that the engine is pushing you forward, right? So the angle here would be 0 between these two, because you're moving this way and you're going that way. So we would have power of 60 pounds times 80 miles per hour. So we would have, what is that? 8 times 6 is
48,000.
4,800 or 1,000? 1,000. Uh-oh, what unit? Yeah, it's miles per hour pound. Or miles times pounds divided by hours. Okay, we don't like those units. But that is a unit of power. Now, that is not the unit of power that your engine is measured in. That's measured in horsepower, which is a very arbitrary measure. The power of a horse. Literally, it was the power of a horse. How quickly a horse could lift a certain amount of weight. Like they would have a rope behind the horse and it would be hooked to a pulley and the weight would be like down in a well. And the horse would take off running and they would, or depending on how heavy it was, running or walking, and how quickly the horse could pull that up, they measured the unit of power, or horsepower, from that. That's literally where it comes from. Okay? All right, so we don't like this unit. So what would our units be in? What are our units for force be? A Newton. And that's meters per second. But what's a Newton meter? Do you remember? That's a joule. So this is a joule per second. So our power is in joule per second. Joule per second, they give a name. It is a watt. Or just W, capital W, which is unfortunate because it looks like work and it looks like weight. All right, so power is in units of watts. So now we have two equations for power so far. Here's equation number 1. Power equals work over time. Equation number 2 is force times velocity, which you can, technically cosine theta. Thank you. You can actually rewrite this one as F delta R cosine theta over delta T, but that's really the same as this one. Okay? And then there's one more, because what does work do?
Changes energy.
Work changes energy. So the amount of energy change over change in time is also our third and final way to figure power so far. We'll actually have about 3 more ways to figure out power once we get to electricity. Okay? But these are our mechanics ways to figure power. All right? So hang on. Got a question for you. So let me get my trusty lunchbox out again. All right, so I take my lunchbox, and so I do this. All right, how much power?
0.
Aw, why? Because there's no net work done. Because I did positive work, negative work, positive work, negative work. Or you could say, well, the total energy change of the lunchbox was 0. So therefore, 0 divided by time, it doesn't matter, it's 0. Okay? So there you go. Oh. Okay, so there's our power. Let me see if I've forgotten anything. Power, power. Where's power? There's power. That's it. Okay, so those are our 3 ways to figure power. So now, last new thing. Actually, do I have any questions on power? Can you answer question 2 now? Let's answer question 2. A person is pushing a box across the horizontal surface at a constant speed of 0.5 meters per second. The box has a mass of 50 kilograms and a coefficient of friction of 0.25. Uh-oh. There's our uh-oh. We got to use past knowledge to solve this. Okay, power. Work over time. Change in energy over time. Force times velocity cosine theta. All right, so which one of these seems like the most appropriate way to find out our power? This one? I think so too, because they give us velocity. So let's try it. So our velocity is 0.5 meters per second. Does they give us any indication that we have an angle to worry about?
No, it's
Okay, so horizontal, so this should be 1, right?
Yeah.
So all we have to find is our force of friction, and then we'll have our power, right?
And this is 0.25.
Ooh, but they give us, okay, we got to go back to last year here. You're pushing something across the floor, so push. What other forces are there? Friction.
Gravity.
Normal. Gravity. All right, so power supplied to the box is going to be our pushing force. But our pushing force is equal to friction, right?
Yeah.
If we're pushing at a constant speed, does everybody agree with that? Everybody remember that if you push with more than friction, it'll speed up. If you push with less than friction, it will slow down. And if you do the Goldilocks thing of pushing just right, then everything stays the same, right? Same velocity the whole time. All right. So, whoa, how do we figure out friction? Mu force normal times 0.5 meters per second. Drat, so what the heck's, we know what mu is. Mu is what, point what, 25?
Force of the normal we can solve for.
Ah, very good, because normal force and mg have to be the same. Because once again, we're in Goldilocks land, right? Where the up force and the down force just perfectly balance. So the floor knows to push up on me with a normal force because I'm flexing the electron structure downward. I'm sorry, I'm flexing the solid structure, atomic structure downward. Okay, so this is mg. Okay, so what's m? Do we know m?
Yeah. 40 kilograms.
40 kilograms. So 40 times 0.25 times 0.5. Whoa, what's g?
9.8.
Okay, in a multiple choice question, what do you put instead?
90.
Negative.
You don't have your calculator, so what do you put instead of 9.8?
10.
To make the math simple, you put 10. All right.
You don't use calculators.
Oh, did I not mention that? Oh, no. All right, so here we go. Here's the rules for the exam. I think I've said it already. On the multiple choice portion of the exam, this is the way the AP exam is, that's the way we'll test. You get the multiple choice first. You get your constant sheet. You get your pencil, you get your eraser, you get your brain. Hopefully that's enough. On the free response portion, you get your calculator back, you get your equation sheet, you keep your constant sheet, so you have everything except your neighbor. Okay? All right, so that means on the multiple choice portion of the exam, all the math needs to be as easy as possible, right? So therefore, every time you use G on the multiple choice, you will use 10. On the free response, you got your calculator, so you use 9.8. All right?
What about other constants and numbers we're supposed to know? Do we also round those?
All right, so here's the deal. By the way, I don't know if we ever came up with our answer, but whenever you get your answer here, it will be within rounding, okay? So most of the numbers on the constant sheet will be numbers that will be, you'll find out will be relatively easy, or they'll just be in symbol form. If you pull out your review packet, you notice that some of the answers are numbers, but some of the answers will be in symbol form, right? And they're in symbol form simply because you don't have to do the math then. You just have to rearrange the equations, okay? Does that help out?
Yeah, that sounds good.
All right, a couple other things while we're on this topic before we get into simple harmonic motion. I believe I told you this already, but there are only 3 triangles on the test. They are the x square root of 2, 45, 44, 45, 90 triangle. We got the 30, 60, 90, where that's x. This is x, or it's 2x. This is 2x. And this is x square root of 3. And then our last one, which is the 37, 53 degree one, and that's a 3, 4, 5 triangle. Okay? So that's all you'll ever get on the multiple choice. And those angles are on your constant sheet. So if you need to find the cosine of 37, it's on your constant sheet. So everybody look at your constant sheet so you're aware that it's on there. And so you know where it's at. Constant sheet is that orange piece of paper. Okay? So if you need to find the cosine of 37 or the tangent of 60, all of them are on there already. Okay? So that's why sometimes our answers are, we'll have like a square root of 2 in the answer or something, instead of numericals, decimals. Okay? To make the math simpler. All right, any other questions about the exam? Yeah?
Oh, nothing exam, but the problem.
Yeah.
So the U-looking thing, whatever it's called, that's the coefficient of friction?
That's the coefficient of
And
friction.
then Fn equals mg?
Yes, because they're equal and opposite in this case. There's only one up and there's only one down, so they must be equal because it's not accelerating up and down. right? And by the way, you notice how they made the math simple here? Look. What's 40 times 0.25? 10. So you got 10, and you got 10, and you got a 0.5, right? So what's our answer? 50. 50 what? Watts? Is that right?
Yeah.
50 watts. Okay. So they try to make the math at least reasonable. Now, I'm not saying that all of them are going to be easy, because they're not. Some of them will take more time than others. Okay? Another quick thing, and this is new for this year. I'm not sure if I told you this or not. The rules for the multiple choice have changed on the AP exam. The rules are that we no longer have a guessing penalty for multiple choice. So you need to answer them all.
So is
Okay?
that just for physics? Or?
That's for all AP tests. That's brand new. So it's weird. It's going to be a different game plan. Because last year and the years before, your game plan was to answer the ones you really knew, skip the ones you didn't know, and the ones in between, if you could take an educated guess, you'd guess. But now, the game plan is to guess on all of them. I'm sorry, to give a good answer on all of them, right? You guess. I pick C. All right? Oh, by the way, that's another thing. Students will do this on the exam. They'll say, oh, my last 3 that I answered were C, so my next one can't be C.
No.
Yeah, failure is correct. I'll give you a hint. No offense, those last 3 that you just answered C, they're probably all wrong. So don't base your next answer on those previous 3. Okay? Answer each question individually. Okay? It doesn't matter what went before. It doesn't matter what's coming up next. You answer each one by itself. Okay? All right. Everybody on the multiple choice is going to be very important. Very, very important that from now on out, since there's no guessing penalty, that you answer them all. If you're running out of time, you answer them. Okay? That means you put an answer in. You just put an answer in. Yes?
Does that mean it's going to be harder to get a 3 or a 5?
No. What they're going to do is statistically they've gone back and figured out how that would have changed the previous scores. So the score on the exam should be the same. They say the reason they're changing it is because it favored the guessing penalty favored students that took a chance and punished the students that were more cautious. So the risk takers were rewarded and the cautious students were penalized.
Well, see, that's kind of redundant though, because the risk-taking one could also get it wrong and get it counted off.
Yeah, but what they found statistically is that risk takers will generally be able to eliminate a couple answers.
If you can eliminate one answer, then you have a 50-50 chance.
Well, if you can eliminate one answer, your statistical chance has gone up. And if you can eliminate 2 or 3...
If you eliminate one, it's a 50-50 chance between how many points you'll win and lose. Because you have a
25%
and
it was
chance getting it right,
right
and winning 1 point. So as long as you can eliminate 1 or 2, I guess.
Yes. Actually, that's what I always told my students. I said, if you can eliminate a couple, for sure, you need to guess. Take your best shot. But what happened was they found that guys would more likely take the risk, and girls would... See? See? And the girls were more likely to go, well, I'd better not, and to be more cautious. And so, statistically, it was lowering the girls' scores by several points on the exam, as opposed to the boys. So they're going and changing it. This is why males die at a younger age. Let's talk about simple harmonic motion. Simple harmonic motion. Okay, this is one of the natural motions that you see over and over again in nature, so that's why we study it. There's another really big reason why we study simple harmonic motion. Simple harmonic motion is whenever you have a equilibrium and a restoring force. Okay, so you have to have two things. Equilibrium and a restoring force. Okay? Okay, what does equilibrium mean again in mechanics? Everything is equal. No. Well, yes, maybe. But no.
No net change.
Everything's constant. Everything's constant.
Okay, wait a minute. Right now, am I in equilibrium right now?
Nothing's changing.
Yeah.
Your eyes are moving.
Consider my body as a whole. Consider only my center of mass. Am I in equilibrium?
Your little Mexicans are going to
Equilibrium and a restoring force. Okay, everybody, equilibrium. Equilibrium in mechanics means that the sum of the forces on the object equals 0. Now, since F equals ma, what does that mean for the acceleration? It's going to be 0. And so what does that mean for your velocity? It's either going to be at rest, equilibrium at rest, or a constant velocity, right? That means either at rest, staying at rest, or, well, at rest at least for that instant anyway, or it's the velocity equals a constant. Actually, rest is a special case of velocity equals constant. It's velocity equals 0, right? So technically it's the same. This is a subset of that. Okay, so in simple harmonic motion, there has to be a place where the forces all cancel. So the acceleration is 0, and where at least momentarily it's at rest. And there has to be a restoring force. And so, in simple harmonic motion, an example of that is a mass on a spring. And I'm going to make this horizontal. So assume it's on a table, okay, so we don't have to worry about gravitational changes. So right here, where the spring is just stationary and not pushing to the right or left, we call that x equals 0, and all the forces cancel out. That's our equilibrium position. Okay, equilibrium position right there. Now what happens if you stretch the spring to the right? There's our equilibrium position. A restoring force means that it tries to get you back to equilibrium. So does the spring do that? Sure. The spring pulls this way. So the spring force is this way, back towards equilibrium. And then it will accelerate back towards equilibrium. But what happens when it gets to equilibrium?
Why are you going to keep
What will be the forces on the block right here again? 0. But it's moving. So right here, all the forces add up to 0 here and here. So there's no acceleration, but it's moving, so it overshoots this spot. This is the equilibrium position. So it overshoots, and then it compresses the spring over here, and it eventually comes to a stop. But now it has a force this way, restoring it back to equilibrium again. Okay, simple harmonic motion will occur then, because what happens is the force is pushing it to equilibrium, but when it gets to equilibrium, there's no force to stop it yet, and so it overshoots, and so it oscillates back and forth across equilibrium. In theory, in our imaginary physics world, forever, right? Yeah. Now, in the atomic world, it certainly is forever, because the atoms in your body are vibrating back and forth, and they will vibrate forever as long as you have some temperature,
Until you die.
even when you die.
Oh,
No
yeah.
such thing as that.
If you die at absolute zero, then yes, they'll stop.
That's how I plan to die.
You plan to die at absolute zero? You're a very silly, silly boy.
No, I'm serious.
All right. Okay, listen. All right. When you speak, your vocal cords go into simple harmonic motion. Hey, because when you speak, your vocal cords vibrate out, and then your tissue pulls them back in, and then they vibrate back and forth. That helps to vibrate the air, right? Musical instruments operate on simple harmonic motion. You hit a drum, the drum vibrates through equilibrium. You play a guitar, the guitar string vibrates across its equilibrium position. You play a musical instrument. When you play your musical instrument, like a saxophone, you set up a vibrating air column. Okay? So, all types of repeated motion can be modeled with simple harmonic motion through a mathematical technique called Fourier transforms. Now, you won't study Fourier transforms in high school, and you may or may not study them in college, depending on what you study. But just so that you know, this basic motion of back and forth, the simplest of all harmonic motions, okay, can be used to model all types of harmonic motion, no matter what kind it is. Like even your heartbeat, you've seen an EKG, right?
Yeah.
Okay? That's a wave, and you can model that with simple harmonic motion. Okay? All waves can be modeled with this. All right? So this is why we study. Okay, now everybody, let's talk about the energy in simple harmonic motion, because that's what we're interested in. Okay, out here, what kind of energy does it have?
Potential.
What kind of potential?
Spring potential.
Spring. When it's right here, what kind of energy does it have? Kinetic and spring potential, right?
Yes.
When it reaches equilibrium, what kind of energy does it have? Kinetic only. And then when it goes all the way out here and comes to a stop, it's turned back all back into spring potential. Now spring potential is 1/2 kx squared. If you were to graph that, it would look like this. Here's your potential energy. Here's your x. Here's the equilibrium positions. And out here, these are the amplitude. Okay, positive amplitude and negative amplitude. And your graph would look like this, except our graph would only end right here, because that's as far as it would go, right?
Yeah.
Okay, so even though the graph goes like this, ours would oscillate between here and here. Okay? Now wait a minute, as it oscillates back and forth, what happens to the total energy of the system? It stays constant, assuming no friction. So if I put total energy, let's see, potential energy in purple, let's put total energy in green.
Mr. Berman, there's the restroom.
Sure. Total energy has to stay constant, back and forth like this. So wait a minute, so what's kinetic energy going to look like? Like, what? Where's kinetic energy zero?
It's just.
At the ends,
kinetic
right?
energy is the area between
Oh,
the
kinetic.
line and the other is the
Here?
area
It's upside down.
between the line.
And where's kinetic energy max?
At 0.
Now will it translate between the two in a linear fashion?
No. Same fashion as the other, yeah.
So if you're in calculus, you see this area,
I know.
and you see this purple area?
Overlap.
No.
Do you see how the value here and the value here will always add up to be the green value, right? Nice. Excellent. So you're going to oscillate between the two values. Okay? Very nice. All right, so there's our energy in simple harmonic motion. So you're just oscillating between one and the other. Now, I'm just going to throw this in because we're in this section. The time period
Spring.
The time period T for a spring mass system, simple harmonic motion, is equal to 2 pi square root of L, no,
M over K.
M over K.
I disbelieve. L was pendulum.
Yeah, I did the wrong one. Okay, this is how long it takes for it to go out and back, or to complete one cycle. So M is the mass, K is the spring constant. Okay, so what's the difference? The spring that's in your little ink pen, is that a high spring constant or a small spring constant? Small. And the springs on your cars are big spring constant, right? Okay, so let's think about that for a second. If I have this mass and I hook it to your spring in your ballpoint pen, or I take the same mass and I hook it to the spring in your car, and I set them moving back and forth, which one will go back and forth faster?
The small one.
Well, this one has a big spring constant. This has a small spring constant. So if the spring constant gets bigger,
Then it's a smaller number.
then you get a smaller number over here, right? Okay. So what if we do the opposite? What if I have a spring here, and I hook this mass to it, and I have the same spring here, but I hook this mass to it? Which one has the longer time period?
The big.
Okay, because if the mass gets bigger, then that's going to get bigger. Now if I double the mass, will this double?
No.
I'd have to quadruple this mass, right? Because it's square rooted.
Yeah.
Quadruple the mass and I get twice the time period, right? Alright? So there you go. That's the time period for a pendulum. But wait a minute, what if I want to know the frequency of a pendulum?
You mean a spring?
I'm sorry, spring. Sorry. For a spring mass. How is frequency related to time period? Anybody remember? Yeah, it's 1 over the time period. So if you want to know frequency instead, you just take this and flip it over. Okay? All right, any questions? Okay, let's do one last object that exhibits simple harmonic motion. If you take a mass on the end of a string and you let it oscillate back and forth, okay? All right, can you please identify the spot? We'll call this A, B, and C. Can you identify the spot where you have equilibrium?
B.
Okay, this is our equilibrium position, because if I set it there and let go, it'll stay, right? Okay. Okay, what's the restoring force over here?
Gravitation.
Just some of gravity, though. Not gravitational potential, but just
Oh, yeah.
gravity, right? So I have a tension here, and I have gravity here, and what happens is part of this gravity is canceled by the tension, but the other part pushes it back this way, right? Okay, so our restoring force is part of gravity, but when we get to this spot, the gravity no longer is pushing it one way or the other, right? So over here, gravity's pulling it this way, over here, gravity's pulling it this way. So that's our restoring force. Okay, at what location will I have maximum potential energy?
A and C.
A and C. But will it be spring like last time?
No.
No, it's pendulum.
Okay, now it's going to be gravitational potential energy, right? And here I'll have kinetic energy, right? Okay, it's going to oscillate back and forth. So potential to kinetic to gravitational potential and back. All right? The time period for a pendulum, by the way, this is L, the length. Technically, the length goes from here to the center of mass. All right? And this is the angle theta that you release it from. Okay? The time period for this is 2 pi square root of something over something.
L
over G.
If the length gets longer, it'll take longer to go back and forward. And if you take it to a planet with more gravitational acceleration, it'll move faster. So on Earth, we don't have real control over G unless you take it in an elevator. If you take it in an elevator and accelerate up, it'll go faster. If you take it in an elevator and you accelerate down, it'll go slower. Now, only during the acceleration phase of the elevator. So, Not when you're going at a constant speed. When you're going at a constant speed, it goes normal.
Well,
Yeah, that sounds
normal.
Yeah. So if you put it on like, a rocket, and you launch the rocket up, it will go faster as it's being launched. All right. Hey, but wait. Here's a good question. What if you have this pendulum out here, and let's say the radius equals, here, let's do this with symbols, just to mess you up. The radius is r, and I want to know, when it reaches the bottom down here, what's the velocity of it right here at the bottom? The mass is m, the length of the string is r, it goes from here to here, and let's say that angle is theta. All right, everybody, I want you to figure out v. What's the velocity at the bottom?
You want us to find velocity, what do you think?
I want to find the velocity, v, at the bottom. It starts from rest. So it starts up here at rest, and it ends down here with velocity. Okay? The comment was made that it's purely kinetic at the bottom. So it's kinetic down here. What kind up here? Potential. So this looks pretty easy. Can we use conservation of energy? E1 equals E2. So it's this at the top, and it's this at the bottom. So what next?
We need to find first the change in height,
M's go away. Ooh, okay, here's our dilemma. So far it's been really straightforward.
Yeah, you have to do this.
So V equals 2GH square root, but our problem is what's H? Is H equal to R? Oh, I heard somebody say the key. We have to make what? Yeah, we have to make ourselves a triangle here. Where is H? This is H. How the heck do we find H? Ah, we find H because this from here to here is R. This is H. So what is this from here to here? That is R. What is it? Cosine theta. Does everybody see that? Now this is really tricky because this is a really simple problem until you get to the H part, right? This is a classic physics B problem because they're trying to make something a little more challenging for you. So R cosine theta, this side of the triangle, plus H must equal R. Therefore H equals R minus R cosine theta. And if you're in your math class, they'd be happy with you if you did this. But we don't care in physics because that is exactly the same as that, right? So you have to take this and plug that in here for H. So it becomes 2G R minus R cosine theta, and the whole thing square rooted. Whoa, that's an ugly square root.
Show is.
There we go. Show is. What is that? Move.